All right, so last week we talked about measuring, or really writing down the right number of digits when we're measuring something. So if you have something like on this guy, right, we're measuring to really the hundredths place. So it's got markings to the tenths place. And you go one farther and you estimate that one. And part of the reason we do that is so that we know the number of significant figures, which is what we're going to be talking about today. So when you're counting significant figures, probably just want to write these rules down, put them on flashcards, and memorize them. Because they are, you can miss, I won't say a lot of points at once, but you can miss a lot of points cumulatively over the course of the semester by getting significant figures wrong. For example, in the unit analysis worksheet, part of that is to use the correct number of significant figures when you do each of those conversions. So our first one is that all non-zero digits are significant. That one's pretty easy. Interior zeros. So if you have, like here we have the 4 and the 2, each on either side of a 0, that 0 is significant. Same with this one here, or the one over here in the 50.1, right? It's got numbers on either side greater than 0. If you have trailing zeros, or zeros to the right of a non-zero number, then those are significant if there is a written decimal point. So here we have a written decimal point, we have a 1, and then this 0 is significant. In this case, we have 500, but it's 500.0, and that 0 is significant because it's after the decimal point, or because we have a decimal point. So then to go through, I guess for each of these, and I should say the actual number of significant figures, for this first one, this is 3 significant figures. These are leading zeros, which we haven't exactly talked about yet, but they don't qualify, they're not interior zeros, and they're not trailing zeros. So we have 1, 2, 3. This is significant because it's a trailing 0, and we have a decimal point. Our interior zeros, so we have 1, 2, 3, 4, 5 total significant figures. Then on the 50, we have 3, 5.10, 3 significant figures again. I'll write these out. Right, 5, 3, 3, and for this last one, there's 4. Because you count all of those zeros because there's a decimal place. Oh, sorry. No, that's fine. What do you mean by assumed?
Like the in 0, that's not just like assumed that that's a 0?
It's,
You get what I'm asking?
yeah, so the last digit is the one that is estimated. So this could have been 500 point, or actually I should say it could have been 499.95, but it gets rounded up. If you're using, if you're measuring this on something that had that level of precision, right? So this gets rounded up, then it's 500.0, and we know that that was, that there's some error in that last 0. So it could be 1 down or it could be 1 up. There were other questions. No, sorry, I didn't mean, yeah. Just those 3 are. Just this, the last one is. Because these front zeros are just telling you how far away from the decimal point you are. They don't reflect anything about the precision of the measurement.
Yeah, and then what happens if there's like multiple zeros, like it doesn't show like ongoing zeros if it's after the decimal?
That's the level of precision.
Okay, got it.
Yeah. So if you had,
Like
right,
500.0000000.
yeah, or 5.000000000, all of these are significant because they're. It could happen. It could happen. That would be an incredible level of precision, though. Yeah, so exactly. So if you had like 0.0001, that's one significant digit.
Why?
Because again, these are leading zeros. Leading zeros aren't important.
No matter the decimal.
Yeah, trailing zeros only.
So for example, if it were like 5.0110, then they would all be significant instead of
Correct.
they would all be significant.
That would be 5 significant figures.
And this is because of rounding purposes.
This is because of keeping track of precision.
Right, okay.
Yeah. And so we'll get how,
Can you just do one more example of a non-zero digit are significant? Because I'm not really understanding that one either.
okay, so if you did, oh, you're not understanding,
The non-zero digit.
that's, so any number 1 through 9. So we could have, well, let's do it with fewer zeros, right? We could have, just like this one, right, where we've got 5 and then a bunch of numbers after it, or a bunch of zeros after it. It could be 5.11111, right? So we could do all these ones. Those are all significant. Or it could be 1, 2, 3, 4, 5, 6, 7, 8, 9.
Okay, got it. I think I'm just like wondering why 0.0 and then that zero that's in the 10th place, that's why it's not significant. That's why I'm kind of confused.
Gotcha. And yeah, it's just because it's a leading zero.
Got it, okay. But if
So-
it was a real number, then it would be significant then.
Yeah, so if this was 0.1110,
Right,
then we'd have 4 significant.
okay, got it.
Yeah.
So, in the instance of scientific notation, the leading zero won't be accounted for.
Exactly. Yeah, so and then I was going to get to this. We would talk about, yeah, that's the next slide. So, right, so trailing zeros before an implied decimal point are ambiguous. This is not exactly the point I was getting to. Like you were saying, if we skip down here a little bit, right, we have this 0.0005. If we convert this into scientific notation, and this is the best way to do it, we would just have 5 times 10 to the negative, and we're moving it 1, 2, 3, 4 places. 5 times 10 to the negative 4. So if you're ever unsure of the number of significant digits, and it's, you know, a really tiny decimal number or a really large number, convert it into scientific notation, and you'll get rid of those leading zeros or unimportant, really trailing numbers, and we'll get into that a little more. But this is a point I want to make because my class this summer just sometimes they just couldn't. For some reason, there were some students who just couldn't grasp this. If there's no decimal point, the number of significant digits is ambiguous because we do not know which one of these zeros for this 50,000. We don't know which one of those is the level of precision. So it could be that we measured to the 10,000ths place, and so we should write it as 5 times 10 to the 4. And that was our level of precision. Or it could be that it was 5.0 times 10 to the 4. Or 5.00 times 10 to the 4. You can't tell because there's, you can't tell because we don't have a decimal place. And we need those zeros to space it out to 50,000. The reason this isn't true for decimal numbers is because the first digit that's significant is always a non-zero number. Because it's only the numbers after that first non-zero number that are significant. So we can automatically exclude these from being significant because they're just placing us farther as a smaller decimal number. So remember that. If there's no decimal point, ambiguous significant figures. If there's trailing zeros, like 10 or 50,000. Yeah. So an example of the 350, right, so this is 3.5 times 10 to the 2. Or if we wanted to show that there are 3 significant figures, we write 3.50. And again, it really follows the same rules that we covered before, where all trailing zeros are significant if there's a decimal place. Give me 1 second. Okay. Is everybody at least okay on that? We'll do, oh, go ahead.
So number 4, 50,000 would have 5 significant figures.
No, it would be ambiguous. So if you wanted to show that it had 5 significant figures, you would write 50,000 decimal.
Okay, so significant figures are only relevant when there's decimal.
Only when there's trailing zeros before the decimal, or before the implied decimal. So,
Example of that?
yeah, for sure. So we could do,
Unknown for 50,000? Is that just unknown?
it would be unknown if there's no decimal place,
Or ambiguous?
or ambiguous. Ambiguous is the word that I'll use. That's your key word there. But for example, 10 is also ambiguous. If we wanted to make it not ambiguous, then we would write 10 decimal place. That's not ambiguous. An example of where we don't have a decimal place, but we still know the number of significant figures would be something like if we had 11, right? We have 2 non-zero numbers, and we know that all non-zero numbers are significant. So there would be 2 significant figures there. Or if we had 101, now that 0 is an interior 0, we don't have a decimal place, but we know that all non-zero numbers are significant and interior zeros are significant. So if it doesn't meet one of the first 2 rules, then you need to be looking for a decimal place. We have a lot of examples too. So at every single one of these, I'll be talking about the number of significant figures, because we also have to talk about how to do math with significant figures. It's not that hard. Okay, so exact numbers, and we talked about this on Monday when we were talking about the number of pennies, right? You have a whole number of pennies, that's an exact number. You don't have, I'm not gonna go there, but if you have children, right, you don't have 2.5 children. You have 2 children or 3 children, that's an exact number. So it's the exact counting of discrete objects, right? We could say the number of students in here would be an exact number. If you had like the number of pencils in your backpack would be an exact number. Integral numbers, also that are not part of an equation. So you could say, if you want to do like a conversion factor with discrete numbers, or exact numbers, I mean, you'd say, say you're trading Pokemon cards, and you want to trade, 3 Pikachus is worth 1 Clefairy. I don't know how to spell Clefairy. That's definitely wrong. But, so then if you were to do 3 Pikachu cards to 1 Clefairy card, those are exact numbers that you're using in a ratio. And we'll see how that applies to atoms later. And there are some defined quantities. One of these is actually an inch. The inch now used to be defined as the width of the king's thumb, but we don't have a king. So the width is now defined as 2.54 centimeters. So if you see 2.54 centimeters equals 1 inch, that is exact. Those ones you just kind of have to know, and usually if you see one of those are going to be, obviously every time they're going to be exact. Right, so some conversions are defined quantities, like this one. Others are not, and I think like a mile to a kilometer is not a defined quantity. Any questions on exact numbers?
Can you just remind what conversion means again?
Oh, so conversion would be, maybe this isn't a super relevant, if you're traveling abroad, right? You have US dollars, and you need to get the currency of Mexico, or pesos or whatever. You're converting your, there's some exchange rate for the day. That's this number of US dollars is worth this number of pesos. And so you're swapping them, and that exchange rate would be, I have no idea what it was. I think it used to be like 8 pesos was $1. No, okay. Yeah. So that's like a more tangible example of like conversion factors. Or you could do cryptocurrencies too. Right, so again, we've got some examples. I'll actually give you a minute to do these on your own sheet of paper so you can compare them, and then I'll go through them in a little bit. We'll just get like a couple minutes. All right, so hopefully you've gotten through a few of those. And so this first one, right, our first rule is that all non-zero numbers are significant. So we've got 4 non-zero numbers. We have 4 significant figures. Our next one, we know that all, again, right, all non-zero numbers are significant. And then if we have a decimal place, trailing zeros are significant, right? And then specifically, zeros that are trailing non-zero numbers. So none of these are significant because they're leading zeros. We have then 2, 5, and then 0. All 3 of those are significant, right? And again, if you wanted to convert this into scientific notation and make it a little bit easier, you would move this over 1, 2, 3 places. So you get 2.50 times 10 to the negative 3. All right, and so then it's a little easier to see. For this next one, 2.7, again, all non-zero numbers, but you don't count these guys. I'll highlight them in red. These don't count in your significant figures. So don't count those in your significant figures. They're just there, similar to the way we're using zeros on B. Right, we're using these zeros to space it to the right of the decimal point. This is just representing those insignificant zeros. So we have 2 non-zero numbers. That's 2 significant figures. This next one, and this is the thing to remember. So all metric conversions are exact. So 1 millimeter, or 1 centimeter here, is exactly 1/100th of a meter. So let's write this out in like regular number notation. So I'll have 2, 7, 0, 0, 0. So now we have 3 trailing zeros. And you don't put a decimal point there because they're not significant zeros. I'm trying to think of a better way to say it than that. If something's written in scientific notation already, that's already telling you where the significant figures are. Yes. Yeah. Yeah.
Even if it's a negative inside of the scientific notation?
Right. So if this was 10 to the negative 3, we'd have 0.123. Did I do that right? Yeah, 1, 2, 1, 2. No, I didn't do that right. All right, so we'd be moving this over 1, 2, 3. So this would be 0.0027. Right, so it's still 2.
So like big picture, it's just like the rest of everything doesn't matter, right?
Yep. Yeah. If it's in scientific notation, that's why if you convert it to scientific notation.
So it's saying, so it's like
Yeah.
the scientists are like, we don't need this.
Yeah,
Okay.
exactly. Yeah, right. So then on this next one, it's only 1 significant, or actually, I take that back. It's not 1, it's infinite. Infinite significant figures, because it's exact. So you could say that there is 1.02 infinity zeros after that, because it is exactly 1.
If that were on a quiz and we were to put exact number instead of infinite, would you accept that? Would it be basically?
Yeah, I mean, it'll probably, if it's on a quiz, it'll probably be multiple choice. But I could see myself putting both of those, maybe? No, I probably wouldn't. I don't like that. But I think the idea here is I want you to, yeah, I would look for infinite. So if you have the option, it's infinite number of significant figures. Why? Because it's an exact number.
So all exact numbers are infinite.
Yes.
So that's going to be all metric conversions.
All metric conversions, yes, have infinite significant figures. Right. Okay, so for this next one, all right, again, all non-zero numbers, those are significant, so 5 is significant. And then if we have a decimal place, which we do, then numbers trailing a non-zero number are significant. So we have 3. Now, on this next one, does anybody want to take a guess? Ambiguous. Good. Ambiguous. Cool. Any other questions there?
So what's the difference between infinite and ambiguous?
Ambiguous means we don't know how many significant figures there are. And the whole infinite and like the infinite number of significant figures for exact numbers becomes important when we start doing math with numbers. Because we want to be able to reflect significant figures in calculations. We want to be able to reflect that level of precision throughout all of our calculations. So when numbers are used in a calculation, the result is rounded to reflect the significant figures of the data. So for calculations involving multiple steps, you only round the final answer. So you'll do all of the math. You'll do all the math. You want to keep track of the number of significant figures at each step, but you only round the last number based on the total number of significant figures. So that'll prevent small rounding errors from affecting the final answer. This happens a lot. Most of the time, it's not a big problem, but there are some times where you do something like dividing sometimes, taking square roots, and if you're off by just a little bit, those errors get magnified throughout the calculations, and you end up with the wrong answer, even though you had all the right numbers, but because you rounded in between, you and I won't get the same answer. So, when we're using multiplication and division, I think these are the easiest, because the result of your multiplication or division carries the same number of significant figures. I should highlight these. Right? So we have the same number of significant figures as the factor with the fewest significant figures. So really, when you're doing multiplication division, all you have to do is look at all of the things that you're multiplying, figure out which one has the fewest significant figures, and then you round your final answer to that number of significant figures. So for this example, again, non-zero numbers, right? So for 5.02, we have 5 and 2, right? Those are significant. And what were they called? Enclosed zeros, or zeros between two non-significant numbers, are also significant. So we have 3 there. For 89.665, they're all non-zero numbers. Makes it really easy. So we have 5 significant figures. And then for our last one, right, again, all non-zero numbers. And then if we have a decimal place, numbers trailing the last non-zero number, those are also significant. So we have 1, 2 there. So our final result then should have 2 significant figures. And sometimes this is going to feel really weird because you're going to get a number like 45.01183. And you'll be like, how can it be right that I'm rounding this to 45? But that's the correct answer because it reflects the precision of your least precise measurement. So if these were like the dimensions of a really weird skinny box, our lowest level of precision is this 0.01. And so that is the highest level of precision that we can report our answer to. So our worst measurement is the most precise we can be about our final answer. Because right. When you're multiplying, yeah. So if you take all these measurements, then there's a lot of error, relatively speaking, in that 0.10. And so we need to reflect that in our final answer. Otherwise, it's, I guess, technically like scientific dishonesty, because you're lying about how accurate you were with your measurements. All right, so division works exactly the same way. And again, just because this is, I know definitely at first, even back when I took Chem 1 here, struggled with significant figures sometimes. It's just one of those things that's a super foreign concept that's hard to grasp. So every single one of these times, I'm going to say non-zero numbers are significant, right? So this one, again, easy. All non-zero numbers. We have 4. This next one, We have our non-zero numbers, we got 2 of those, but also we have a decimal place, so our zeros trailing our last non-zero number are also significant. So we have 3. And again, we'll take this number and we round it to the lowest number of significant figures, which is 3. So I'm going to put a 0 here because I like to. 0.966. Right? And this 0 in front is not significant. But it can be hard, or it can be easy to miss that decimal place, so I usually put 1 in front.
In the first one, if that zero, the answer, if that zero was not a zero and it was like a one or something,
Round down.
no?
Every equation that we're gonna see like this, and we're gonna have to figure out the significant, is it always gonna be the very last part of the equation?
No. Right, so yeah, in both of these, yeah, the last number was the one with the least number of significant figures, but it doesn't matter the order. Yeah, so if you had like a long string of, if you did both of these together, if you did all of this multiplication and then you divided by each of these, then it would be the smallest, which would be 2 still. Yeah. The 9 makes the 5 go to a 6. So we've done, right, we have 3 significant figures that we're working with. So we have 1, 2, 3. And then we take this last digit and we round it, up or down. Right, so if that was, 4 or less, then we would round it down, and this would stay 0.965. And sorry, what was your question about the 0 after the 45.0?
If it was like a one or an actual number, would it then be, well, I guess not because
Yeah, it's still
no
2
matter
6.
what, you're still only going to do it.
So the only thing that would change is if this was, whoops. Right, so if this had been 45.91183, 1, 2, right, and then we're rounding that last digit. Yeah. So then this would be 46.
I'm just not understanding how that's not important. You get what I'm saying? Like,
Right. Yeah.
this is a, yeah.
It feels bad to throw away all those numbers. You worked so hard to get them. But they're not significant. You should have done better when you measured that 0.10. Sometimes that's just a limitation. I mean, if you're using the same thing to measure all of these, it seems like you could have gotten, based on this 0.665, you could have gotten another digit there, but you didn't for whatever reason. Okay, so moving on. Rounding, use only the first or leftmost digit being dropped to decide in which direction to round. Ignore all digits to the right of it. So this goes back to what we were just talking about. So and then you round down if the last digit dropped is 4 or less. You round up if the last digit dropped is 5 or more. And then again, you only round the final answer. So if we did, actually let's go back to this. If we did this math, right, and we did it out by hand for whatever reason, because we lost our calculator and our phone and our computer and maybe the calculator watch if you have one. If you lost all of those things and you're doing this one by hand, and you had 5.02 times this 89.665, right? You do that math, you figure out what that answer is. You don't round that. You take that number and then you multiply it by whatever the whole number is times 0.10. And then that gives us our final answer. Once you get to your final answer, that's where you round. Otherwise, you will have rounding error. Like I said, sometimes it's not a big deal. Sometimes it's a $125 million mistake. So, again, right, so we're only using this is, honestly, this wording here, I forgot to change the slide. This wording here is confusing to me. Right, so it's the last digit that's being dropped. Well, it's the leftmost digit that's being dropped. Let's do examples. It makes more sense that way. So if we have 2.33, and we're using 2, and we say we got 2 significant figures, we need to round this. So we're dropping the 3. Because we dropped that 3, it's 4 or less, so we round down. We end up with our answer of 2.3. If this digit is 7, so we got 2.37. Again, just to use two significant figures here. Then we round up. And what it means by the leftmost digit is if we had, 3.41645, and we want two significant figures. By the way, if I write sig figs or type sig figs on any of your assignments next to something, that means you got them wrong. So we want two sig figs here. So we're going to do 1, 2, and we don't care about any of the rest of this. We only care what that 1 is. So, or if this was even, so we'll round this down, right? So this would be at 2 sig figs, 3.4. So even if this was 3.499999, doesn't matter what those other 9s are. The only one we care about is this first one after the one we drop. Or maybe in another situation where it might be a little bit less clear if it was 3.44999, right? Because if you rounded this 9 up, then that would make this 5, and then you would round that up. But again, with two sig figs, we don't care about these. Cool? Okay, so again, I'll give you a couple minutes till like 5:47. If you want to keep working on the other ones, go ahead. But I'm going to start working through these up here. And so we got, again, our first one, right? Non-zero numbers. Numbers trailing a non-zero number if we have a decimal place. We got 1, 2, 3. Non-zero numbers, very easy. 3. Remember, we don't count leading zeros. We don't care about them. So here we've got a 0 that's between two non-zero numbers. And we have non-zero numbers. So we've got 4. This one, we only have leading zeros. So we only have one significant figure. And then our last one, non-zero numbers are all significant. I should underline that. We got 2. So you should have ended up with just one lonely significant figure. And if I punched this into my calculator right, 0.001. On this next one, similar thing. Again, all non-zero numbers are significant. That's 4 there. Again, all non-zero numbers, and then a trailing 0 after a decimal place. So we've got, that's 6. And then non-zero numbers again, 3. So here would be a good example of where the lowest significant digit is not the last one. Again, if I type this into my calculator correctly, right, our smallest number of significant figures would be 3. I'll box this one too because that was 1. And so we've got 0.20. I'm going to do this before I rounded, just to also show the rounding, right? 0.2038. We'll throw a couple others on there. But we only want 3 significant figures. So let's go ahead and underline those. So we're rounding 8 up, because it's greater than, or it's 5 or greater. 0.204 would be your answer. Oh, that actually reminds me. On your homework, and really on any assignment that you turn in, please put like a circle or a box around your answer, and then a circle or a box or something around the question number. That helps me out a ton. Because sometimes it can get real messy, when you're doing a lot of work, and I can't find where the answer is. It may be obvious to you right after you did the math, but that helps me out. So, any questions on those? Yeah. Oh, that's the lowest number of significant figures. So when we round at the end, we use the lowest number of significant figures to determine the number of significant figures of our answer. Yeah. Cool? Let's start saying sig figs from now on. Significant figures is a mouthful. Okay, so that's multiplication and division. addition and subtraction are a little different. So for addition or subtraction calculations, the result carries the same number of decimal places as the quantity carrying the fewest decimal places. So if we're doing this first example, it actually doesn't even matter so much how many sig figs each of these has, because it just matters how many decimal places. So based on this, we could just do this math real quick. So 4, right, 6, 11, carry the 1, 8, 16, 22, carry the 2, 7, 9. Right, so 9.214. The fewest number of decimal places is going to be, should just 5.74. Okay, it'll just show up. So when we round this to get our correct number of significant figures, we get 9.21. That would be our correct answer. And again, this is one of those things where it can feel really bad if you didn't get enough precision on one of your measurements, but that's just how the cookie crumbles. So if we have our 4.8 on this next example, we're subtracting 5, 6, 8. Wow, I had to remember how to do like longhand subtraction like that. So we get 0.865. But again, we're using the smallest number of decimal places. And that, in this case, happens to be, oh, no, it is different than any of the others. So it's going to be 0. We're just keeping the 8. So our next digit is 6, so we round up. So it's going to be 0.9. Yeah. Well, actually, I think we're going to have another example on the next page. Are there any other questions, though? Did I do that math wrong? Oh, because these are zeros. Yeah, like I said, I didn't remember correctly how to do it. All right. What was the answer? Okay, so similar thing, but now our last digit is 3. It's 0.8 would be the answer, right? Because 3 is the last, should erase those. Those are implied zeros. Because if they're not written out, they have to be there to do the math. I forgot that they existed. I'm sorry, zeros.
Question about like if an implied, like.
Yeah, I just did the math wrong.
When you're doing math, it's implied.
It's implied.
They're not significant, but they're significant enough to be implied.
Right.
Okay.
Yeah, and like honestly, aside from and this will be a surprise for anybody who has lab today, aside from that math quiz, you get to use your calculator on everything. So you're not going to do longhand like this. You're going to do 4.8 minus 3.965 on your calculator, right? So then, in this situation, they're not lined up super nicely for you. If you wanted to, you could. But this is still the fewest number of decimal places.
So in addition and subtraction, you're going to still use the lowest number of significant figures in the equation.
No, you use the lowest number of decimal places. Right, because 4.8 has 2 significant figures.
Right.
I said I was going to use 2 sig figs. Sig figs. So it has 2 sig figs, but our answer only has 1. This is 0.8. So for multiplication and division, count the sig figs of all the numbers that you're multiplying or dividing together, and it's the smallest number of sig figs. For addition and subtraction, and again, we'll do more examples. So it's the fewest number of decimal places. I guess it should be fewest number of significant decimal places. We'll get to that. So again, 28, so I don't mess up again, I'm going to use my calculator. 28.02. 28.02 minus 0.99. So we're going to get Yeah, right. So the answer, this is what we did on the last one too. But you have this, you may have a smaller number of significant figures, sig figs, than you did in your two numbers that you're adding or subtracting. So here the answer is going to be 0.03. So how many sig figs is that? It's just one. One lonely sig fig. All right, so again, take a shot at these. Okay, so hopefully it didn't take too long to type that into your calculator. I guess you might have been writing it down. But, all right, so these are the raw numbers coming out of the calculator. We're adding or subtracting. Use the smallest number of decimal places. The reason I said significant decimal places is because of things like this 1.5870. This is a significant decimal place because it is a sig fig, but in this case, it's more decimal places than the smallest. So we round to the smallest number of decimal places, which is our 1.8. I'll do an example right now of the zeros. And so we're going to round to the tenths place, one decimal place. 7.5, and then because this next digit is 8, we're going to round up. So we're going to get 7.6 as our final answer. On this next one again, we go through and count all these. So there's 3 decimal places, 2 decimal places, and then 3 decimal places again. So our final answer then will have 2 decimal places, not significant figures, 2 decimal places. So we're going to do, we ignore everything before the decimal then. This one's, we're going to keep this decimal place and this decimal place. And then because this last digit is 8, we're going to round that up. So we get 131.11. Cool? So if we had, for example, this 1.1000 plus 0.3. Actually, let me do it like this even. 0.30. This is what I mean by significant decimal places, right? Because each of these is a significant decimal place because it is a sig fig. And same for this 0.30. That's also a sig fig. So our smallest number of decimal places in this case would be 2. And so our answer would be 1.40, 2 decimal places. Cool? All right. Got a lot of ground to cover in 30 minutes. So what happens then if you have multiplication and division and addition and subtraction in the same math problem? You'll do the steps in parentheses first. So this is like, please excuse my dear Aunt Sally, PEMDAS, it's order of operations. So do the steps in parentheses first, determine the correct number of significant figures in the intermediate answer without rounding, and do the remaining steps, then round the final answer considering the number of significant figures in the intermediate answer. It's just, I know that sounds confusing. Again, we've got examples. Actually, I'm just going to go ahead and say this one more time first before we actually do the steps. Right? So it's order of operations. So you're going to do the steps in parentheses first, determine how many significant figures that is, right? You should write it next to it or something, circle it, put a little star next to it, smiley face, something. And then do the remaining steps, keeping those significant figures in mind, and then you do the rest of the steps and determine what the answer is going to be, your final answer, based on that intermediate number of significant figures. All right. So if we have, because we didn't get like another example, I'm just going to go do A at least. So, start with what's in parentheses. We're going to start with a subtraction. So addition and subtraction, we're going to use the fewest number of decimal places. So just identify those. We have 2 here, and we have 1 here. And so we'll do that math. And that will give us 330.42, right? Not rounding here. But we determine our number of significant figures, because it's addition and subtraction, the fewest number of decimal places. So this is our last significant digit, which means we'll have 4 significant figures, because these are all significant. So we're going to do 4. I'm going to draw a little smiley face next to it. And then we're going to multiply now this intermediate number with that insignificant 2, poor 2, times the rest of our problem, 3.897. And we'll get, put it over here, 1287.64. I'm just going to write all these out for 674. So our intermediate step had 4 significant figures, sig figs, and we're multiplying it by this 3.897, and that has, again, all non-zero numbers are significant, 4 sig figs. So both of them have 4 sig figs, so our final answer should have 4 sig figs. So then our final answer will be 128, and then because this is our last digit, the 7, we're going to round based on the next digit. So this will be an 8. All right, so take a shot. Oh, sorry, question. If there aren't parentheses, then follow the order of operations, right? So in this example, if we didn't have parentheses, we would do the multiplication first. Yeah. So this is an example. The parentheses, at least here, are just to make it a little bit easier so you know which ones to do first.
Where did you get the 4 and the smiley face?
That's the number of sig figs for our intermediate number. Because we have 1 decimal place here, we have 2 decimal places here, so we use the smaller number of decimal places, so that's the 4. So then everything before the 4 is significant. Because if we were to stop here at this point, then our answer would be 330.4. So that would have 4 sig figs. So then in our next step, we carry along that 4 sig figs, but we also bring the 2 because we don't want rounding errors. That was your question? Yes. So you take the whole thing along, you're just counting the number of sig figs you have in your intermediate step. Cool? Clear as mud? Let's see. Okay, so this next one then. Actually, here, let's do this. So, let's say that we didn't have those parentheses. I'm just going to do it over here, but I'm going to zoom in. Right, so it was, 3.897 times 782. No. No, that's just a coincidence. So you will have to check those intermediate steps. So if we're looking at this now without those parentheses, we follow the order of operations, we're going to do 3.897 times 72.3. Was it divided by? No, it's multiplication. Oh yeah, the next one is division. Yeah, this is the first one again. So here, we're going to count the number of sig figs, right? All non-zero numbers, so there's 4 there. I should use a different color. 4. And then we're counting the sig figs here. That's also 4, right? All non-zero numbers. So we're going to multiply 3.897 I think the key to note here too is that even though the number of sig figs is going to be different, your answer is also going to be different because you're multiplying before you add. So if you don't use it, it's a different question than really. Anyways. Right, so. So we got 3048.6231. And because we're multiplying, we're going to use the smallest number of sig figs. Both of these were 4. So we're going to have 3048. We're keeping 4 sig figs. And again, we're going to do the 4 with the smiley face. So we're going to keep 4 of these sig figs, but we're going to use this whole number for the next step. And so we're going to end up subtracting now 451.88. Write it this way, 451. This class ends at 6:20, right? 6:25? Oh. It'll end when I say it ends. 2596.7431. And because we're subtracting, we're going to use the smallest number of decimal places. So this is 2, 4. And so we're going to use the 2 because that's smaller than 4. So it's 2596.74. That would be our final answer if we did it in that order. Right, so if we do it, oh, we used the 4 sig figs. Oh, I guess in this case it didn't matter. Yeah, it didn't matter that it had 4 sig figs because we did, right, because then we did subtraction and then all that matters is the number of decimal places.
So it kind of just matters the last step to do, whether it's division, multiplication, or subtraction, or addition.
Kind of, because you could be like alternating in between, theoretically. You know, so you really, if you're doing multiplication and then you're doing addition, subtraction, then it doesn't really matter what the per sig figs are, just the number of decimal places. Or actually, wait. No. I goofed. Well, these aren't significant. They're not significant decimal places because we only have these 4 sig figs. And so these are the ones that determine how many significant decimal places are, because if we stopped, right, we would round up to 6, but we would get 3,049. What was your question? Well, so the answer actually would be that this has, let me erase these 2.
It would be 3048.
Oh, this was
the
1.
whole number minus 451.
So you would still subtract 3048.6231, but only our significant decimal places, and again, this kind of gets back to like why some zeros are significant. We don't have any significant decimal places because these are our significant figures. These last ones are not significant figures. So it's 0 significant decimal places. So then our answer would be, actually I shouldn't have erased this whole thing.
You can get sig figs for intermediate answers and it not affect your final answer.
No, it does affect your final answer because the answer for this one would be 0 decimal places after the subtraction. So it would be 2597 because we're rounding to 0 decimal places. 7 because we're rounding up. You subtract the decimals too. So if I had done this without the decimals, I'm not sure if it'll change this specific one. So if I leave the decimals off, then we get, yeah, I mean, it changes just a little bit, but that's how rounding errors are. So I'll do it in a different color. So if I used just these 4 numbers, so let me just to differentiate. In this one, I did the math with all of them. And that was this answer. If we just use those 4, 3048 minus 451.88, then it's 2596.12. And again, we're still saving just 4. Well, we're not saving any decimal places because it's still zero significant decimal places. So it would be 2596. So the rounding error in this case is you just be off by 1. Most of the time, yes.
Okay. But we want precision, so.
Yeah, you want to be doing it right.
Yeah, so I was gonna ask you, because if you do like 30, 40, right, and you round it up to 349, you get that answer, 2597.12.
Yeah.
You want to make sure before subtraction.
Yeah, so this is an example where the rounding error is not super big. The easier mistake to make, and this is starting to get a little bit messy here. Can I just add a, no. I can do it over here. The easier mistake to make would be instead of not doing all of this, what were those numbers? Oops. 6, 2, 3, 1. All right, so the easier mistake here to make is that you would end up with this 3048.6231 as your intermediate, and then you just do that subtraction. Oh, didn't do it. 8.6231 minus 451.88. And then you write down, your 2596.7431. And then you say, okay, out of these 2 numbers, which one has fewer decimal places? And then you would end up with, I'll leave myself enough room here. Right, so we've had 2 decimal places because of the 0.88. So 2596.74. And this is the common mistake to make. This, you would lose points for sig figs. And, here, the ways that I did it, we ended up with the same number of sig figs, but this is too many sig figs. It should end up being 4. Yeah, so that's why this 4 was important in the intermediate, because it tells you how many sig figs you have, which tells you how many significant decimal places you have, which is kind of what the next problem is. Yeah. This was just an example to say if we did the multiplication first, and it ended up getting so much more complicated than that. I'll just leave all of that on the slide and try to work around it so that you have it later. So let's look at this next one. If we do this, somebody pointed out that this is basically what we just did. So we do 4.58 divided by, and so we're going to get as the whole number 3.6994559 minus 8. Right. So in this example, we'll end up with 3 sig figs in both. But the difference is that we're subtracting. So because our division, right, we use the fewest number of sig figs. So let's count those. We have 3 here, right? Non-zero numbers. Non-zero numbers again, 4. So 3 sig figs. This is 1, 2, 3 sig figs. The rest of these are not going to be important for determining our number of significant decimal places when we do our subtraction. That's what I missed on the other one. So we'll now do, right, this whole number minus 0.578. And we'll get, back to the black one, 3.1185294559. That's separate. But because in our intermediate step here, we only had 3 significant figures and 2 significant decimal places, well, this has 3 significant decimal places. Our result will have, well, I guess that's sig figs, but our result will have 2 significant decimal places. So we will round to 3.11, and then because this is an 8, we'll round up. 3.12.
So I
Yeah.
did the significant, I used the significant figures in the subtraction part of this problem.
Uh-huh.
And I got the same answer, that's just constant.
So you used,
I used 3.0
oh, because,
as my, to subtract.
yeah, that's just coincidence. So you used 3.6 or 3.70. Yeah, that's just coincidence. Yeah. But like I said, right, sometimes those errors are really small. But if you do those errors over and over again, if you've got multiple calculations that you're doing, they'll start to add up. And most of the time, if you're off by, like that last significant digit is off by 1, right? So if this was 3.13 or 3.11, in terms of getting the correct answer, I won't mark you wrong. But in terms of having significant figures, well, in this case, you'd be same number of sig figs. But if you're off by sig figs, then you'll lose half a point, generally. Okay, I think this goes till 3:20. Oh, it is, or 6:25, huh? This gives us 6 minutes to get over there into lab. Okay, what's next? That's a fine place to stop. This stuff is important. That's why I just like take as much time to do this as possible because it'll make everything else easier because it's going to involve this and all of it. So, yeah, take 10 minutes, and then I'll see half of you in lab.